हेलो गाइस, मेरा नाम अमय है and I am a student of IIT Bombay from the Mechanical Engineering Department. I am currently in my fifth semester and today we will be starting with integral calculus. So why is calculus an important topic that we must study? So as we all know that calculus was initially designed to calculate areas, volumes, arc lengths, etc. As a part of mathematical improvement. Uh, then in physics, it is also used in calculation of forces and bending of beams, which is an important part of structural engineering. It is used to solve differential equations in electrical engineering, for example, in the RLC circuits. And it is also used in spaceflight mechanics to determine orbital path, velocity, acceleration, and other parameters. In the industry, we can use integral calculus to study growth and decay models, which are often used in medicine to study bacterial growth and effects of drugs when they are applied to the body, and also population models to study the population growth or decay. In economics, it can be used to study supply and demand curves. Then it is also used in acoustics in the musical industry, in data analysis to maximize efficiency and productivity, and also used to solve the famous Navier-Stokes equation for video game simulation. And it can be used to compute weather patterns such as increase or decrease in temperature, humidity, etc. So now to start integration, we will first have a look at the fundamental theorem of calculus. So we know that integration is defined as the area under any curve. So suppose we have this curve y is equal to small f of x. We define the area function as capital F of x, and we can see that between a certain x and an x plus h, this excess area can be defined as f of x plus h minus f of x, which can be approximated by this rectangle. So the width is h and the height is approximately f of x. So dividing this thing by h, we can see for the limit h tending to 0, this is nothing but the derivative of capital F of x. So we define our integral in the limit, starting limit a and the ending limit b as this. And if we integrate this, we can write the integral as f of b, which is the value of the area function at b, minus the value of the area function at a. Now I will discuss some basic properties of integrals. As we all know, if we change the upper and if we switch the upper and lower limit, we get a minus sign outside the integral. If there is some value c belonging to a comma b, then we can split the integral as a to b and b to c. Then if f of x is a bounded function between some value small m and capital M, then we can say that the integral will lie between the two rectangles where m into b minus a gives the rectangle formed by the lower bound, and capital M into b minus a gives the rectangle formed by the upper bound. If we have two functions f and g such that f is less than equal to g, then the integral of f will be less than or equal to integral of g. Now this property can the next property can be analyzed using the graph. So we have that mod of the integral is less than mod of the function an integral of that. So we can see if we have some function like this, we know that if the function is above the x-axis, the value of the integral is positive, and negative if it is below the x-axis. But in case the mod of the function is taken, the entire function will be above the x-axis, so it will always be positive. Hence this value has to be greater or equal to the other value given. This property is a alternative form of the famous Cauchy-Schwarz inequality, which says that if we have an integral, the product of two functions, and this is squared, then this will be less than or equal to the integrals of the individual function squared. Now I will talk about some formal definitions of integration. So first we will talk about Darboux integrability. Here we divide the interval a to b in n parts, x0, x1, x2 up till xn, and we define this partition as p. So now we'll define two parameters, small mi and capital Mi. So capital Mi is defined as the supremum value of fx in the interval xi minus 1 and xi, which is basically the maximum value the function takes in this interval. Similarly, small mi is called infimum, or the minimum value of the function in this interval. Then we will define u and L, which is the upper sum and lower sum, which is estimated by summing all the rectangles for x belonging to xi minus 1 to xi. So lower sum will obviously be the sum of all the rectangles which are bounded by this lower value, and upper sum will be the sum of rectangles bounded by the higher value. As you can see in this graph here, the above graph is the graph for upper sum because the endpoint value is the higher one, and here the endpoint value is the lower one, so this graph is representing the lower sum. So a function f is said to be Darboux integrable if the upper sum is equal to the lower sum, or in terms of epsilon we can define it as this: if mod of upper sum minus lower sum is less than epsilon, then the function is Darboux integrable. So we define this value to be the integral of ft. Let us look at a quick example. If we have to prove the Darboux integrability of the function fx equal to x over the interval 0, 1. So like I said, first we have to divide the interval into n parts. Here we are taking all parts to be equal. So the interval xi will be I by n, and as I varies, we'll get different xi. For I equal to n, the xn value will be 1. So lower sum is defined as the lower value and into the rectangle, the width of the rectangle. Since fx is an increasing function, the minimum value will be taken by xk minus 1. So when we put this value here, we will get k minus 1 by n, because I said that each xi is given by I by n, as we can see in this partition over here. And then we know the summation for this. K is a constant, so we will we can sum this and we will get this. For the upper sum, we know that the upper value or the supremum is at x equal to xk, because this is an increasing function. So summing this, we will get this answer. And now we need to find the upper sum minus lower sum by this criterion over here. So we'll get 1 upon n. So for any epsilon greater than 0, we can see that the partition Pn satisfies this inequality, which is the condition for Darboux integrability. So this function is Darboux integrable, and now this integral can be calculated normally, that is 0 to 1 x dx, which is equal to half. Or we can also take the limit of this for n tending to infinity, which is also half. So thank you for watching this video. Please scan this QR code to know more about us, and I'll see you all in the next video. Thank you.